Okay, so I want to make a few remarks about this proof, which says that there are no non-constant global regular functions on a projective variety. There's only one issue with this proof, namely that I need that y intersection ui is non-empty for every I. Okay, and what I want to say is that given a y a closed projective subvariety of projective space, it could happen that y may not intersect a certain ui. Okay, and therefore in that case we reduce to a case, we can reduce this n, okay, to come to a situation where y is embedded in a projective space and it intersects every ui. Okay, and how we can do that is by realizing that if y doesn't hit a certain ui, then y is completely contained in the complement of that ui, but the complement of that ui is the locus where xi vanishes, and the locus where xi vanishes is a projective space of one dimension less. Okay, so y is embedded in a projective space of one dimension less. Okay, and you can therefore you can work in that projective space. Now that projective space will again have an affine cover, and you check whether y intersects each of those members in an affine cover. The moment it does not intersect one of the members in the affine cover, it means that it is again contained in some hyperplane in that smaller projective space, which is again a much more smaller projective space. So you can continue this process will have to stop at some stage, giving rise to a y embedded in a suitably smaller dimensional projective space with the property that y intersection ui is never empty for every I. Okay, so that is the case that we have treated. Okay, so with that in mind, this proof covers all the cases. Okay, that is something that you have to notice, right. Okay, so the point is that there are no global regular functions on a projective variety, alright, and as you can see the proof needs the notion of it needs the notion of the function field. Okay, without the notion of a function field you cannot give this proof. Okay, so what I am going to do next is I am going to go back to this issue about projective varieties, that that there is no proper analog of the affine coordinate ring for the projective case. So for the projective case the analog of the affine coordinate ring is the projective homogeneous coordinate ring, but the big deal is that while the affine coordinate ring is an invariant of the affine variety, the projective coordinate ring, the homogeneous coordinate ring of a projective variety is not an invariant. Okay, so to explain that, what I am going to do is I am going to look at a very simple situation. So I am going to do the following thing. So I'm just going to take, I'm going to describe what is called the D-uple embedding. Okay, so the D-uple embedding. Okay, so the idea is the following. So what we are going to do is we are going to take projective n space. Okay, and then so you fix D positive integer. Okay, and well, I'll also fix n, so let me write fix n and D integers. Okay, and I'm going to take Pn and I'm going to embed Pn into P capital N, okay, where capital N is n plus D, choose D minus 1. Okay, so so what's this number? So you know the homogeneous coordinate ring of Pn is polynomial ring in these n plus 1 variables. Okay, and now what I'm going to do is that I'm going to look at monomials in these variables, but all of degree D, this given degree D. Okay, so let m0 etc. up to m sub n be the monomials of degree D in x0 through xn. Okay, so each mi looks like you know x0 to the power of m0 into x1 to the power of m1 and so on xn power m sub n with summation of all the mi's equal to D. Okay, you're just writing out monomials of total degree D. Okay, I mean products of all these xi's, powers of xi's, such that the powers add up to D, and how many such monomials you will get, you can check that these many monomials is what you will get. Okay, I mean n plus D choose D is what you will get, and therefore you know if you look at the homogeneous coordinate ring of this bigger projective space, it will be k of y0 etc. up to y capital N. Okay, and this n is just this n plus D choose D minus 1, right? Yeah, so then the number of monomials will be this much. Okay, and if you label them as m0 through mn, you are actually getting n plus 1, and that capital N plus 1 should be this. So this is the number of monomials of degree D in small n variables. Okay, now what we are going to do is we are going to define a very nice map. So this is the this is a map from Pn to it's a monomial embedding, so it's Pn to Pn, P small n to P capital N, and we call this as, we use the word phi D, I mean we use this, let's use the symbol phi sub D, and what we are going to do is the following thing. See, any point here is of the form lambda naught etc. lambda n. This is how a point here looks like. These are the homogeneous coordinates of a point in projective space. Okay, and what you're going to do is, it's very simple, you're going to send it to this point where these small n plus 1 values are substituted for these xi's, okay, in the right order in each of these monomials. Okay, so that you get you get capital N plus 1 coordinates which will define a point in whose homogeneous coordinates will define a point in the bigger projective space. So you know let me write it as m0 of lambda naught etc. lambda n blah 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 and it will go on up to mn of lambda naught etc lambda. Okay. So this is the map. See, you have lambda naught through lambda n, and then you give me a monomial like this, you substitute for xi lambda I, okay, and you do this for each of these capital N plus 1 monomials, you will get these capital N plus 1 coordinates, take the point, and of course these are the monomials in some order, okay, some order. For example, you can use lexicographic order on the powers if you want, okay, you can use the lexicographic order on the variables and their powers, right. You can have some suitable order. After all, this is a finite set, so you can choose a decent order. So this is the map, okay. Now the question is, now the point is the following. The point is that this map embeds the smaller projective space as a closed subvariety of a bigger projective space, okay. This is a closed embedding, okay, that in other words this map is an isomorphism of its onto its image, and the image is a irreducible closed subvariety of a bigger projective space, okay. And so, well, so what is that, so how does one see this? So the first thing that one notices is that, you know, if you take so you know you define whatever is happening here in terms of coordinates can be reinterpreted in terms of commutative algebra in terms of the corresponding homogeneous coordinate rings. So what we have is, we have for this we have a map in this direction, the opposite direction, and mind you this is so I will call this as phi d upper star, okay, because it is going to induce in some sense pullback of regular functions, okay, via phi d, okay, and this is, well, k y naught yn, and this is k x naught xn, okay. And what is this map? This map is very simple, you just send yi to mi. The map is pretty simple. After all, there are exactly as many yi's as there are mi's, okay. So send the corresponding yi to the corresponding mi. So what this map does is that it takes, mind you, this yi is degree 1, alright, whereas this mi is degree d, it is a degree d monomial, okay. So what this map does is it takes every degree 1 thing to degree d, alright, and therefore this is called a graded homomorphism. So what it will do is it will take the degree 1 piece to degree d piece, okay, and it will take the degree r piece to the degree r times d piece, okay. You know, if I, instead of yi, if I put yi power r, it will go to mi power r, and the degree of mi power r will be rd. So this is what is called a graded homomorphism. Mind you, these two are graded rings. We are not thinking of them as affine coordinate rings of the affine spaces above, no, we are thinking of them, the reason why we put this s is to keep reminding ourselves that there is a gradation that is going on, and this gradation is very important whenever you are working in the context of projective varieties, okay, in this case they are projective spaces. So phi d upper star of, you know, if I take s r, the degree r part p and k, this will land inside s dr homogeneous part of the small p and k. This is what it does, it takes, so you know, this is what is called a graded homomorphism. So it is graded, we say it is graded of degree d, phi d star is a graded k algebra homomorphism of degree d, okay. This is what it means, it takes the any degree L piece to the corresponding L times degree L times d piece, okay. And it is a fact that if you take the kernel of a graded homomorphism, it is always a homogeneous ideal, it will be a graded ideal, it will be a homogeneous ideal, okay. So the fact that this is a graded homomorphism will tell you that its kernel, a kernel of a homomorphism is always an ideal, but the fact that it is graded will tell you that the kernel is a homogeneous ideal, okay. So this will imply that kernel of phi d star is a graded ideal, is a homogeneous ideal. I mean I am just saying that, you know, if a polynomial here goes to 0, okay, I am just saying that if a polynomial here goes to 0, which is the same as saying that a polynomial belongs to the kernel, then every degree d, I mean every homogeneous part of that polynomial also individually has to go to 0. That is because, you know, if you take the polynomial and take any degree L part, that will go to a it will go to a degree LD part, okay, and therefore if the image is 0, then you will get that each homogeneous part of the polynomial goes to 0, you know. So it is very easy to verify that if f is in kernel phi d star, okay, and f is sigma f sub L equal to 0 to some m, okay, where f L belongs to S L, okay. This is the breaking up of f into its various homogeneous parts. S sub L is the degree L homogeneous piece of this big Pn, okay. Then, you know, phi d upper star of f 0 will be phi d upper star of f, that will be equal to just sigma L equal to 0 to m phi d upper star of fl, okay. But you see this phi d upper star of f sub L, this will belong to S sub Ld of this Pn, small pn, okay, and as L changes these are all in different pieces, and this, so you know these are all pieces in various different degrees, and if the sum is 0 then each piece has to be 0, that is what direct sum means. So whenever a polynomial is 0, then every homogeneous piece has to be 0. So and these are the different homogeneous pieces of the image phi d upper star of f, okay. So what this will tell you is that phi d upper star of fl is 0 for every L, this is what it will tell you. And so what you are saying is that if phi d upper star kills f, then phi d upper star kills every homogeneous component of f, and that is precisely the same as saying that if f belongs to kernel phi d upper star, then every homogeneous component of f also belongs to kernel phi d upper star. That is another way of saying that kernel phi d upper star is a homogeneous ideal, okay. So and you also notice that the kernel is also a prime ideal. Why? Because the image is a domain after all. So the moral of the story is that this kernel of phi d upper star is a prime ideal, it is a homogeneous prime ideal, and therefore its 0 set will define a projective subvariety, a closed subvariety of the bigger projective space, and the claim is what is that closed subvariety of the bigger projective space? It is actually the image of this, okay. So further, kernel phi d upper star is prime since S P small n k is a domain, target is a domain, okay. So the 0 set of kernel phi d upper star inside the big projective space is yes and is a subvariety, so projective variety, it is an irreducible closed subset, okay. And the claim is that the image of phi d is exactly this, the claim is the image of phi d is exactly z of kernel of phi d upper star. These are the claims, and the second important claim is phi d from this little Pn to, if you restrict it to the image, is an isomorphism of varieties. So this is the claim. The claim is that this phi d, the so called D-uple embedding, it maps this variety projective space isomorphically onto a closed subvariety, and that closed subvariety is nothing but the zero, it is the zero set of the kernel of this homomorphism. Okay, and so this is a claim, alright. This requires a little bit of computation, okay, but before we try to settle these claims, I just want you to look at the case when small n is 1, okay, and d is 2, okay. That is the simplest case, and the reason why we often look at that case is to tell you that you can have two projective varieties which are isomorphic, but their homogeneous coordinate rings are not isomorphic, okay. So take n equal to 1, d equal to 2, okay. If you take n equal to 1, d equal to 2, then you have p1 k, you have phi d, this is phi 2 into p, well here I am going to get so I will get 3 choose 2, which is the same as 3 choose 1, which is 3 minus 1, this is 2, I am going to get 2, so it is p1 inside p2, okay, and and I have this z of kernel of phi 2 upper star inside this. So I just want you to verify this for the case n equal to, n equal to 1, d equal to 2 is the simplest case, alright. To verify it for the general case we will need further calculation, but there is a lesson to be learnt even in this simple case, okay. So how does one ensure this? So so what is a map? The map is lambda 0, lambda 1 goes to the monomials in you are looking at monomials of degree 2 in 2 variables, okay. So so you have x0 and you have x1, so the small n is 2, so you have x0 x1, and then you are looking at monomials of degree 2 in x0 and x1, so you get m0 which is x0 squared, you get m1 which is x0 x1, and you get m2 which is x1 squared. These are the 3 monomials you will get, alright. And therefore what is this map? You are going to send lambda naught lambda 1 to lambda naught squared, lambda naught lambda 1, lambda 1 squared, that is what this simple map is, okay. And what is this phi 2 star? This phi 2 star is the map that is going to go from S of p2, which is just identified with k of y0 y1 y2, to S of p1, which is k x0 x1, and you know what this map is. You are just going to send y0 to, well, according to this definition you are going to send y0 to m0, which is x0 squared, y1 will go to x0 x1, and y2 will go to x1 squared, okay. So are you able to see that? Right. And what is a kernel of let us calculate kernel of P2 star. What is the kernel of P2 star? Well, kernel of P2 star, you can see this. Y0 is going to x0 squared, y1 is going to x1 squared. I have crammed up everything here. So y1 is going to not x1, sorry, and y2 is going to x1 squared. Okay, you can easily see that y1 squared minus y0 y2 goes to 0. Okay, so this contains the ideal generated by y1 squared minus y0 y2. Okay, because this is going to go to 0, and if some element is in an ideal, then the ideal generated by that element is also in that ideal. Mind you, this is a degree 2 element, so it is a homogeneous element, so the ideal that it generates is a homogeneous ideal. It contains in this, it is contained in this. And in fact, if you use some commutative algebra, you can show that this is exactly this kernel. Okay, so see, the reason being that this is irreducible. y0 squared minus y1 squared minus y0 y2 is an irreducible polynomial. Therefore, the ideal it generates is a prime ideal. Okay, and this is a homogeneous prime ideal, right? And the height of this ideal is going to be 1. That's because of that's just because of Krull's principal ideal theorem. Okay, so Krull's principal ideal theorem says that you take a Noetherian ring and you take an element in the ring which is neither a 0 divisor nor a unit, then any minimal prime ideal that contains that element will have height 1. So if you take any minimal prime ideal that contains this, it has to be equal to this because it is already prime, and therefore its height is 1. And since its height is 1, the 0 set of this will define a hypersurface, okay, which is a one dimensional object. Okay, whereas this will also have the same height. Okay, so what this should tell you is that the 0 set of y1 squared minus y0 y2 will contain the 0 set of kernel phi2 star. You will have this, and this guy is one dimensional. This is a one dimensional object. Okay, this is a one dimensional object. That's because if you just look at the 0 set of this in the affine space over this projective space, you will get the affine space over this projective space is 3 dimensional. Okay, and there I am having a single irreducible polynomial, therefore its 0 set above in the affine space will give me one dimension less subvariety, a codimension 1 subvariety, so I will get a 2 dimensional subvariety. But when I remove the origin and come down to the projective space, I will cut down 1 dimension, therefore I will get only a 1 dimensional object. So therefore this is a 1 dimensional irreducible closed subvariety of projective space. Okay, and that contains this. Okay, but then mind you, this is also an irreducible closed subset of projective space, but the point is that this contains phi2 of p1. By definition it contains phi2 of p1 because you take any element, take any point in phi2 of p1, it is of this form, okay, and the fact that the way we have defined phi 2 star will tell you that this is contained inside this, okay. I think that is probably pretty easy to see. Just a minute, I think I just have to write it down. So you know, if G is in Z of kernel phi 2 star, G is say G of, so G is a polynomial in 3 variables y0, y1, y2, then phi 2 upper star of G is 0, that is G of, instead of y0 if I put x0 squared, x0 x1, x1 squared is 0, this is what it means. Sorry, G is just in kernel phi, sorry, yeah. Suppose G is in the kernel, okay, not the 0 set, suppose G is in the kernel, write G as a polynomial of these 3 variables, and then so if it is in the kernel phi 2 upper star of G is 0, so that means G of this is 0. Mind you, this is a polynomial, this is happening in k of x0 x1, that is how this map is defined, okay. So this implies that, you know, if you take a point for a point lambda naught squared for a point lambda naught comma lambda 1 of this P1, we have, you know, G of lambda naught squared lambda naught lambda 1 squared is 0. I mean, if G of some polynomial is 0, then for the polynomial whatever variables you substitute, that also should result in 0. So this implies, so this calculation actually tells you that phi 2 of P1, the image of phi 2, image of P1 under phi 2 has to be in the 0 set of this kernel, because everything in the kernel vanishes on this. Okay, so you know, now what you must understand is that, you know, this is already one dimension, okay, this is already one dimensional. Mind you, phi 2 is a topologically phi 2 is an injective, in fact topologically you can check phi 2 is a homeomorphism, okay, phi 2 is injective actually, phi 2 is injective, it is topologically a homeomorphism, okay. These are all things that you can check. So since phi 2 is a homeomorphism, phi 2 of P1, which is the image of phi 2, is topologically isomorphic to P1, and P1 is one dimensional, therefore this is one dimensional, okay. So that means this is already one dimensional, okay, this will be one dimensional, but this is also one dimensional, and this is a closed subset, okay, and in a finite dimensional Noetherian topological space, okay, if you have a closed subset of the same dimension, then the closed subset has to be everything. In other words, if you go to a proper closed subset, the dimension has to fall. If you go to a closed subset and the dimension does not fall, then the closed subset has to be everything, okay. This happens in a finite dimensional Noetherian topological space, which is the case with all our varieties, okay. So this will tell you that this will tell you that this is equal to this equal to this, okay. So the moral of the story is, so you know, if you use a little bit of topology, then you will get that phi 2 of P1 is the same as the 0 set of kernel of phi 2 star, and that is the same as the 0 set of this, okay, okay. And in fact what I want to say is that see this phi 2, see this phi 2 is actually a, so therefore this phi 2 actually gives an isomorphism of P1 with this 0 set, okay. which is actually the 0 set of y1 squared minus y0 y2. This is the same as the 0 set of y1 squared minus y0 y2. Okay, these two are equal for dimension reasons, and this is an isomorphism of this with that. Okay, and in fact I am saying this is even an isomorphism of varieties. This thing is even an isomorphism of varieties, and you know, the one way to check it is by you know, to check that a morphism has a certain property. It's enough to check it on a cover, a suitable cover of the target, and then you pull back that cover to get a cover of the source and restrict the morphism to each of these members of the cover, and if this morphism has a particular property for each member of the cover, then it has that property throughout. For example, so you know, if I want to show that this map from P1 to the image, if I want to show that it's an isomorphism, it's enough to show it on a cover. And what cover will I use? I'll use the usual cover of P2, which P2 has cover consisting of U1, U2, U3, I mean U0, U1, U2, which are the 3 A2s which cover P2. So you know, I can make a computation involving that. Okay, so well, you know, let's try to do that computation for a moment. So you know, if you look at so you know, I have this P2 here, and I have this, suppose I take U0, then I have this so I have this Z of kernel phi2 star, and then I will get Z of kernel phi2 star intersection U0. So I get this diagram, this is this intersecting with U0. So and you know this is well, U0 is identified with A2 by phi0, you know, and U0 corresponds to the place where Y0 is non-zero, alright, and therefore under this isomorphism this will be identified with a closed subvariety of A2. Okay, and if I take, so I have P1 to P2, I have this phi2. If I take phi2 inverse of this Z of kernel, or I simply take phi2 inverse of U0, it will land inside, so you know, it will land inside this. Okay, so I have U0, U1 and U2, the 3 A2s that cover P2, and I am working with U0, and I am taking the inverse image of U0. Taking the inverse image of U0 under phi2 is taking the same as taking inverse image of U0 intersection Z kernel phi2, because Z kernel phi2 is actually the image of this that we have already seen. It goes like this, the map factors like this. Okay, and mind you, set theoretically this map is you must understand that set theoretically this map is injective. This map is set theoretically injective and it is set theoretically surjective. Okay, why is it set theoretically injective? Because you know, if you have lambda naught lambda 1 and you have lambda naught prime lambda 1 prime, suppose they go to the same thing. Okay, the fact that you have this mixed product here, first of all you will get lambda naught squared is equal to lambda naught prime squared, and you will get lambda 1 squared is lambda 1 prime squared. So the only problem is that you might get it when you take square roots, you could have taken different square roots, but then the fact that this lambda naught lambda 1 is also equal to lambda naught prime lambda 1 prime will ensure that lambda naught lambda 1 you started with should be equal to lambda naught prime lambda 1 prime. You can easily check injectivity, and you can check surjectivity, because you know, any point here is actually here, any point here is actually here, so the square of the middle coordinate is equal to product of the first and the last coordinate. Okay, therefore you can take the square root of the first coordinate, and you can take a square root of the last coordinate. That will give you a point here which will go to that. Okay, if you take the correct square roots. Therefore it's both injective and surjective is a very easy set theoretic checking. Only thing is that you can take square roots because you are in an algebraically closed field, you always will have square roots of elements. Okay, that is where there you need algebraic closeness. Of course, otherwise for all our arguments about varieties we are at the back always assuming algebraic closeness. Okay, so it's very easy to check this map is bijective. It's very easy to check that this map is a homeomorphism. Okay, that's very easy to check. So, but you know the big deal is I'm looking at this map. Okay, what is this map going to do? See, it's the same map. It's lambda naught lambda 1 going to, after all let me write the map above, it's lambda naught colon lambda 1 going to lambda naught squared colon lambda naught lambda 1 colon lambda 1 squared. This is the map. Okay, and the moment I go into u naught, I mean that means that my lambda naught squared is not 0. Okay, and lambda naught squared is not 0 means that lambda naught itself is not 0. The point is that this is an affine variety. Okay, the point is that this is an affine variety here. I need a larger diagram, so let me draw it again. So you know, so I have this P1, so I have this P1, I have Phi2, P2, and I have U0 here, which is identified by Phi0 with A2, and you know what this map is. This map is just something that sends y T0 T1 T2 is mapped to, well, T0 is not 0 on U0, so I will send it to T1 by T0, T2 by T0. This is what this map is. Okay, this is what this map is. And what is this map? This map is lambda 0 lambda 1 going on to lambda 0 squared lambda 0 lambda 1 lambda 1 squared, that is what Phi2 is. Okay, and I am taking, and mind you this map actually factors through the 0 set of kernel of Phi2 star inside this. Okay, which I mean let me just call it Z so that it is easy to write down. So, and if I intersect with u0 I will get Z intersection u0, and that under this isomorphism Phi0 will go into Z0. Okay, and if you follow it up, so you know if I take Phi2 inverse of u0, that is an open set here in P1, alright, and if I now write out this map all the way to Z0, okay, the map will be lambda naught colon lambda 1 going to, well, you see first of all lambda naught comma lambda 1 will go to this, okay, and this will go to division by lambda naught squared. So this map will finally land in if I go all the way to Z0, you know the point I will get is I divide this by lambda naught, so I will get lambda 1 by lambda naught comma lambda 1 squared by lambda. This is the point I get, okay, when I follow it all the way up. And mind you since I am taking inverse image of u0, lambda naught squared is not 0, which implies lambda naught is also not 0, which means actually this thing is actually in the u0 corresponding to this projective space. This P1 also has a cover by two A1s, namely u0 and u1. So you know if so I'll just call them v0 and v1 so that I don't confuse with the u0 here. Okay, so in fact this fellow is inside so this is inside v0, okay, where this v0 in this projective space, this is the open which is identified with A1, by a phi naught here is identified to A1, okay, and this, do not confuse this phi naught with that phi naught, okay. Maybe I can so that you know I let me not call this phi naught, I will call this as psi naught. This is a standard identification of V naught with A1. V naught is a locus where the first coordinate x naught does not vanish, okay, and you see, and under this identification this point here will go to, what is the point it will go to? It will go to the point lambda 1 by lambda naught, okay, and therefore finally if you take this and phi 2 inverse u naught is an open subset of V naught, so its image here will be an open subset of A1, okay, and if you finally write out the morphism is this, and mind you, it is not a, I should not put square brackets, it is round brackets, yeah, here also it is, so these are coordinates in affine space, okay, they are round brackets and they are coordinates separated by commas, okay, not, you use square brackets only for homogeneous coordinates. So you know finally when I write out this for phi 2, if I take the inverse image of u naught from phi 2 inverse u naught to u naught, if I write out the morphism after going to the affine piece here and the affine piece, the corresponding affine piece there, the morphism is lambda 1 by lambda 0 going to lambda 1 by lambda 0 comma lambda 1 squared by lambda 0 squared, that is the map. So the map is simply t going to t comma t squared, that is what that is the map. The map is just t going to t comma t squared, and it is a map from A1 to A2. So when I compute this map phi 2 from P1 to P2, okay, on this affine piece, on this affine A1 where the first coordinate in this P1 is, first homogeneous coordinate in this P1 is not 0, and on the affine piece here where the first coordinate piece, the first coordinate in this P2 is not 0, which is an A2, then, and when I translate this map finally I am getting the map t going to t comma t squared. Isn't that a morphism? That is a morphism because projection on each coordinate gives me a regular function. So projection on the first coordinate gives me identity, projection on the second coordinate gives me t squared, okay. So this is a regular function. So the moral of the story is that phi 2 inverse u naught, see if you take, so phi 2 restricted to phi 2 inverse u naught from phi 2 inverse u naught to its image which is z intersection u naught is a morphism, okay, this is a morphism, alright, and actually the funny thing is it is actually an isomorphism. This is actually an isomorphism because you know if I take this map t going to t comma t squared, that is an isomorphism because you know if there is the inverse morphism which is given by projection on the first coordinate. If I take the map t going to t comma t squared, okay, and if I project on the first coordinate, I will get the projection on the first coordinate will send t comma t squared back to t, okay. Therefore it will, projection on every coordinate is certainly a morphism, alright. So the moral of the story is that I have an inverse morphism such that this followed by this is identity, okay, and where is the inverse morphism defined? I am looking at the graph of I am actually looking at points of this form, and what are these points? These are the points of the parabola y equal to x squared. This is lying, see these are all points on z of y minus x squared. After all t comma t squared is a parametric representation of the parabola, and z of y minus x squared is just, it's a conic, it's a plane conic, it's a conic in A2, it's a parabola in A2, and all the points t comma t squared is, if you vary t, you are simply going to get all the points on this conic. Only thing is t is not 0, okay. No, I can have lambda 1 0, so lambda naught is not 0, but lambda 1 can be 0, so this t can be 0 as well. So the moral of the story is that this map is not just a morphism, it's actually an isomorphism, and in fact an isomorphism. Okay, so what I have proved is phi2, if you restrict to phi2 to phi2 inverse u0 to its image, that's an isomorphism. I did this for u0, you try it and write it down, you do it for u1 and u2 also, it will be an isomorphism. So what you have done is you have checked on a cover that phi2 is an isomorphism, and therefore it is an isomorphism. So phi2 actually gives you an isomorphism of p1 onto z. Okay, so I repeat, what I have proved is phi2 from phi2 inverse u0 to z intersection u0 is an isomorphism. Okay, similarly I want you to check that phi2 from phi2 inverse u1 to z intersection u1 is an isomorphism, you can write it out, and phi2 from phi2 inverse u2 to z intersection u2 is also an isomorphism. Okay, and z intersection u1, z intersection u2, z intersection u0 form a cover of z, because u0, u1, u2 form a cover of p2, and what you have done is you have checked that morphism is an isomorphism on a cover, and therefore it is an because the property of being an isomorphism is a local property. Okay, so what this will tell you is that phi2 is actually an isomorphism of p1 onto z. Okay, so let me write that here. And now I want to state the important point. Similarly, you can check phi2 in restricted to phi2 inverse of ui from phi2 inverse of ui to z intersection ui is an isomorphism for I equal to 1 2, thus phi2 from p1 to z is an isomorphism. Because z is the union of z intersection u0, z intersection u1 and z intersection u2. Okay, so this is why you get that the image of p1 here is this, and it's an isomorphism onto the image. But now comes the big deal, this is also a p1, okay, and that is actually a twisted p1. You know, if you want to think of p1 as a projective line, okay, then the image here you have seen locally it is a conic, it has been twisted into a parabola. So what has happened is this line p1 has been mapped isomorphically onto a conic locally. Okay, but the beautiful thing is, even though these two are isomorphic projective varieties, if you calculate their coordinate rings, the homogeneous coordinate rings are not isomorphic. Okay, that gives us the lesson that the homogeneous coordinate ring of a projective variety is not as well behaved as the affine coordinate ring of an affine variety, it is not an invariant. Okay, so you know, if you calculate the homogeneous coordinate ring of p1, what you will get is, you know, this is just k x0 x1. Okay, and what is the homogeneous coordinate ring of z? It is the homogeneous coordinate ring of the target p2 modulo the ideal of z, and what is that? That is just k y0 y1 y2 modulo what is the ideal of this z? It is just the ideal generated by yn squared minus y0 y2. Okay, and these two are not isomorphic. Even though So see this is a polynomial ring in 2 variables, alright, and this is a polynomial ring in 3 variables, and you are going modulo degree 2 homogeneous polynomial. These two rings are not isomorphic. You can you can try to prove that as an exercise, that this ring cannot be isomorphic to this ring, because actually you know this ring will have the full universal property for a polynomial ring in 2 variables. This won't. That is how you check that this is not isomorphic. This cannot be isomorphic to this, because a polynomial ring has a universal property. This is a polynomial ring in 2 free variables, so it has a universal property, whereas that property will not hold. You cannot find an analog of that property for this ring, and that will show you that this cannot be isomorphic to that. Okay, so I want you to check as an exercise that these 2 rings are non-isomorphic. Okay, as K algebras they are not isomorphic, and therefore the homogeneous coordinate rings of P1 and Z are different, but yet P1 and Z are isomorphic as projective varieties. So that gives us the lesson that the homogeneous coordinate ring of a projective variety is highly dependent on the embedding. Okay, if you take the embedding decides how your homogeneous coordinate ring is going to look like, and the homogeneous coordinate ring can change even though your variety up to isomorphism does not change. So this is the problem, that for projective varieties you cannot keep track of them just by looking at their homogeneous coordinate ring. So to sum up this and the previous lecture, what I want to tell you is that unfortunately with projective varieties neither can you use global regular functions, the ring of global regular functions, for the simple reason it is just constants, nor can you use the homogeneous coordinate ring because it is not invariant, and this is really in sharp contrast with the affine varieties, where the ring of global regular functions is the same as the regular coordinate ring, and that is an invariant. You can completely recover the affine variety from its ring of regular functions is the same as its affine coordinate ring. Okay, but you can't do that with the projective variety. So this necessitates that this problem that you have in which is of interest in higher algebraic geometry, that you take a projective variety. To study it you have to study all its embeddings into various projective spaces and look at the geometric properties of that embedding, of those embeddings, and try to extract more information from those embeddings. Just looking at the homogeneous coordinate rings with respect to the embeddings will not help. Okay, you need to extract some more information. Okay, so that's and usually this kind of study is accomplished by studying so called line bundles and linear systems on which are connected with embeddings, namely morphisms of a variety into projective space, and this is usually done in a second course in algebraic geometry. Okay, so with that I will stop.